Alright, what's up everybody? Welcome back to Structure Free Chicka Chicka Learning! And in this video, we're gonna introduce or explain the principle of work and energy in engineering dynamics. And what we're gonna do is explain where the principle of work and energy comes from. And if time is available, we'll even do an example problem with the pendulum. But here, for the principle of work and energy, let's consider first a particle moving on a curved path. We'll say it starts here at some position. We'll call that S1 along the path. So here, this is the direction of increasing path here. S, like this, along the path here. And then it goes here, S2, some in between right there, and the particle is here. Just give it a circle. This particle is moving along this path here. There are some forces acting on it. Anyways, it's moving from S1 to S2. And when we analyze this using F equals ma, or the equations of motion here, we would say, our positive normal direction would be towards the center of curvature, like this, plus n. And then we would say there's a tangential direction, plus t, if we're analyzing this using normal and tangential components, like this. There would be all these forces that are acting on the particle, and there would be a resultant, right? A total resultant of external forces. We'll just say that that force acts this way, like this. So this is the sum of all the resultant forces acting on my particle, giving it, moving it from S1 to S2 right here. And I can break this up into components right here. We would say, okay, well, shoot, if there's an angle between the path and the tangent, or the angle between the tangent and the force resultant, we'll call that angle theta right here. But there would be a force resultant in the tangential direction, like this. Sum of the forces, the tangential component, like that. And then there would be a normal component, like this, just from breaking it up into normal and tangential components, like that. This would be the external force diagram, and we'd also have this inertial diagram here with the same tangential and normal directions, boom, like this. And we'd have the inertial term MAT and the inertial term MAN, like this. Yes. Yes. Okay. And now, when I look at this, if I ask myself, which of these components, normal and tangential, do work? Well, think about that for a second. All right. So hopefully you have some sense of what work is already. But here, the work, any force that's perpendicular to the path does no work. All right, so let's focus on the tangential component, because that's the component that actually does work, because it's parallel to the path. And so here, if I write the equation of motion, or Newton's second law, in the tangential direction, I would have this sum of the forces in the t equals MAT. And we know from our understanding of normal and tangential components that this acceleration in the tangential direction is like we're looking in a 1D motion case. And so it has our very popular kinematic relationship for a particle, this dv dt. We also know that the velocity of a particle is this time rate of change of position, or this ds dt. And when I combine this and I get rid of time, if I substitute for time, this gives me this other really popular relationship, this a t ds equals v dv, like this. This at is v dv over ds. Okay, and if I substitute for this acceleration in my equation of motion, then I get the sum of the forces in the t is mv dv over ds. I do some rearranging right here, and I'm looking at the particle as it moves from S1 to S2. So this particle has some velocity here, v1, and then at S2 it has some velocity here, v2, like this. And so I can evaluate or set up the integral so that this would be the sum of the force FDS from S1 to S2 equals the integral mv dv from v1 to v2. And what we have here is this component right here on the left is the work. Force times distance, the work it takes to go from one to 2. Work, 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 work. You know what I'm saying? Right there. Okay. And we could put it in terms of that force resultant F here. So here, this Ft, do you see how this Ft is really also, the sum of the forces times cosine of theta, or the component in the tangential direction. So another way that I could have expressed this as well is to say, is like this right here. The sum of the work it takes to go from 1 to 2. And on the right here, if I integrate this right here, this would be 1/2 mv squared evaluated from v1 to v2. And this tells me, if I write this one more time, the sum of the work from 1 to 2 is equal to 1/2 mv2 squared minus 1/2 mv1 squared. And what we have is, in words, this is the work. The total work from 1 to 2 is equal to the change in kinetic energy. And I think everyone here probably knows that kinetic energy is this 1/2 mv squared. And we'll use the symbol T for kinetic energy. So this term right here, we'll call this T is 1/2 mv squared, and we'll call this the change in kinetic energy, which really is T2 minus T1. And then another way to look at this, one other way, which really we're just rearranging and doing some basic algebra, is like the kinetic energy at 1 plus all the work, the sum of all the work from 1 to 2 is equal to the kinetic energy at 2, like this. And so, there are many analogies in life here to the principle of work and energy. College is just one. You know what I'm saying? You come in and you are doing some level, you have some energy or kinetic energy as you're coming in, and hopefully you're doing positive work. There isn't too much friction in your life, and that you'll do positive work and grow, and you'll have even more kinetic energy at the end of college. You know what I'm saying? All right. But in any case, the reason that this is powerful is that because we're dealing with an energy term, these are all scalar quantities. Scalar quantities. So what's powerful about this is that we're able to maybe simplify some of the geometry or the directions, especially in the tangential direction, because we're dealing with energy terms, right? We're dealing with kinetic energy and work, which are all in units of joules. And what we're also doing is that we're also solving, especially in cases where you need to get velocity right away, we're solving for velocity directly. All right. And so we're going to get the speed at a specific point or as a function of something using the principle of work and energy right away directly. One thing to remember is that this is only a substitute for the tangential component of the equation of motion. So usually in problems, use with the sum of the forces in the normal direction, like this. So in many problems, there's two equations, two unknowns. You can replace this with the principle of work and energy, but you will still need to use the equation of motion in the normal direction. All right, hopefully this gives you a good overview of the principle of work and energy and where it comes from. Let's go ahead and do an example problem next. Yo, structure free.